Okay, we're going to talk today about enzyme kinetics. And kinetics refers to movement, right? And so we're going to build equations, right, that describe how fast enzyme-catalyzed reactions move, right? So they're going to describe the rate of these equations, or oftentimes we think of the velocity of a reaction. Now, let's do a little bit of review before we can start to think of an equation that will describe an enzyme-catalyzed reaction. Let's think about rate equations that you looked at in intro chem. So let's think of a simple equation like A turns into B. You might remember that you have rate equations that have constants in them, right? So we could describe the rate of this reaction as equal to the K, little k is the rate constant, times the concentration of something. In this case, let's say that this reaction is dependent on the concentration of A. If we were to graph this reaction, rate versus concentration of A, we'd get some straight line. And some reactions follow these kinetics, right? The more higher concentration of A we have, the faster the reaction goes. And this would be first order kinetics, right? First order, because this reaction is dependent on the concentration of one thing. Okay, well, let's try to do that with maybe an enzyme catalyzed reaction. Here's an enzyme plus a substrate, and it forms a product. That reaction is dependent on some constant. Maybe the rate of something like this would be equal to K times the concentration of enzyme times concentration of substrate. And we would call this a second order reaction, because the rate is dependent on the concentration of two things. Now that would be great, that would be easy, we'd be done, right? The kinetics of an enzyme-catalyzed reaction is dependent on this equation. Now it doesn't work like that, and you may have seen some problems with the way I was doing this to start with. You know, one big problem is the enzyme is not your normal reactant. It's not consumed during the course of a reaction like a normal reagent like A. It doesn't just bump into substrate and both of them add together to form a product. It's a catalyst, and so it's there on the left and the right. And so while this is a good illustration maybe of how we think about rate equations, you know, neither one of these is going to work really well if we're going to describe an enzyme catalyzed reaction. We're going to have to build a new equation in order to describe those. And that's what we're going to do right now, is try to derive a famous biochemistry equation called the Michaelis-Menten equation. And we'll see where it comes from, and we'll try to make the thing. And really, this is a famous equation because it's super useful if you're a biochemist to try to predict how fast, or the rate or velocity of an enzyme catalyzed reaction based on the concentrations of things that you can measure, like substrate and total enzyme concentration. So here's the equation we're going to base the Michaelis-Menten on. We're going to have an enzyme plus a substrate. They don't just go to product. What happens is that they bind together to form an enzyme substrate complex. Now, when the substrate is bound to the enzyme, one of two things can happen. Either they can dissociate to form free enzyme plus the substrate, or every once in a while, the enzyme actually acts upon that substrate to form the product. Now, if we look at this equation, it has some elements of first order kinetics, maybe this part forward, but it also has some second order kinetics. We need enzyme and substrate to come together to form this complex. So it's not going to be that easy to make a rate equation that describes this. But let's finish maybe labeling this equation so we have the tools to derive the Michaelis-Menten. One thing to look at is that this enzyme, what is this? It's either here, or it's here, or it's here. We're going to designate this enzyme here as free enzyme, which means it's not bound in the complex. So we've got enzyme that's either free by itself or enzyme substrate complex combined. Now the other thing is we're going to label these arrows with rate constants. We'll call this one K1, and the reverse K minus 1. We'll call the rate of the reaction that forms product K2. Okay. Now, let's just stare at this thing for a minute, and we're going to write down some things that make sense, some assumptions that we're going to use in order to do this derivation. One is that what's the velocity of this reaction equal to? Well, it'd be cool, really. I mean, all we care about is the formation of product. That describes how fast this reaction's occurring. So maybe we can think of this reaction as being equal to K2 times the concentration of the enzyme substrate complex. That describes the formation of product. So maybe we're done, right? That's a good equation. The problem is, you know, we can't measure how much of this enzyme is free versus how much is in the enzyme substrate complex. Just imagine doing your lysozyme lab, right? You've got your cuvette, it's got cell wall substrate in it, which is the substrate, and you put in some enzyme. You know how much enzyme you put in there, but once it gets in there, you don't know how much of it's free, how much of it is bound to complex. That's a very difficult thing to measure. And so this is not a good equation because it's got something in there we don't know what the heck it is. Okay? Now, what do we know about this enzyme substrate complex? Well, we know that the concentration of the total enzyme, right, the enzyme that we add to the reaction, it's going to go one of two places. Either that enzyme is going to be free, or it's going to be bound to the enzyme substrate complex. And so this might help us as we try to derive an equation based on this that has something we can measure in it. We can't measure enzyme substrate complex, we can't really measure how much of it's free, but we know how much we started with. We know how much we're putting in the reaction, so we know total enzyme. Maybe we can do some fancy substitution to get rid of enzyme substrate complex and replace it with something we can measure. Another assumption we're going to make is that during the course of an enzyme-catalyzed reaction, the concentration of this enzyme substrate complex doesn't change. So I'm going to describe that with an equation. I think I switched markers here, maybe. The change in the concentration of the enzyme substrate complex over the change in time equals 0. That just means that this has reached equilibrium. We're forming enzyme substrate complex at the same rate at which it is dissociating. Okay. Now, the last assumption we're going to use is that there's going to be a maximal speed at which this reaction can occur, a maximal velocity. And that maximal velocity is going to be reached when all of the enzyme that I've added is doing its job. How do we know when it's doing its job? Well, if all the enzyme that we add is bound up with substrate in the enzyme substrate complex, that's as fast as that reaction can go. And so, really, we can describe the maximal speed of this reaction as equal to K2 times the total enzyme concentration. If the total enzyme concentration equals the enzyme substrate concentration, because all of the total enzyme is bound up here, then the velocity of the reaction is equal to K2 times the total enzyme. All of it's here. All of it's doing its job. Okay. With these assumptions and these equations, we can start to derive the Michaelis-Menten equation. And we're going to really build it on this. Our goal is to take this equation that has this problem with it, something we can't measure, and we are going to substitute something in here for the enzyme substrate complex that has things we can measure.